hybridization also affects bond length. So it turns out, if we think from our pictures before, we have our s orbital like this. And if we drew our p would kind of come out and around this on both sides. So we'd see p orbital here, and then the other lobe kind of coming out there, right? So the p orbitals project farther, right? So if this is our nucleus right here, our p orbitals come way out to the end, where the s only comes out to right there, right? So they just extend farther into space. So as the contribution of p orbitals in the hybrid orbital increases, the hybrid orbital gets longer and projects farther from the nucleus. Okay, so if we look down below, that affects the length of bonds. This is how I always remember this thing. So if we look at a molecule like this, and we look at a carbon like right here, that's sp3. So if we're sp3, what percent s character are we? Well, there's a total of 4. That sp3 is made up of an s plus a p plus a p plus a p. And we have 1 that's s. And then overall, there's 4 orbitals, right? So it's s divided by s plus p plus p plus p. So down here below, we have an s plus a p plus a p plus a p, which is 1/4, right? Which comes down to 25% s character. All right, if we look down here below, this atom right here has a steric number 3. It's sp2. There's 1 s, right, divided by an s plus a p plus a p. So that's 1/3. That's 33% s character. So you're higher in s character. That means that your bond should be shorter, and that's the case. 1.53 up here, right, going to 1.34. And if we come down here and we're sp, that has a steric number of 2 because there's a carbon and an H, right? So steric number of 2 gives us sp hybridization. Here we're an s divided by an s plus a p. So that's 1 divided by 2, or 50% s character. And that should be the shortest bond length because we have a larger representation of an orbital that doesn't protrude into space as much as a p orbital. Okay. Now the last thing to talk about here is isomers, and it's just some naming stuff that's gonna show up. Now we've seen constitutional isomers before in this lecture. We looked at the isomers of C2H6O, where we have dimethyl ether, or ethanol here, and then we saw the isomers of C5H12. Right, we saw that. Remember, we classified these carbons as being primary, secondary, tertiary, or quaternary. Now, the other type of isomerism that's out there is something called stereoisomerism. And this is really important. In fact, it gets its own chapter in organic chemistry. And it's conceptually a little bit challenging, but they are isomers that differ only in the arrangement of the atoms in space. So, for example, the molecule over on the left right here, so this is caraway seed oil. If we look at this, and if we imagine that this is a mirror, that molecule is the mirror image over here. It's the mirror image of the molecule on the left, right? Oxygen's pointing in here, it's pointing in here. You got your carbon, carbon out, carbon, carbon out right there. Now, it turns out that these molecules are different because they are not superimposable on each other. So if we rotate our spearmint oil around, then we get this not lining up in the correct orientation. And, it's called spearmint oil, so it smells like spearmint. So these two compounds are the same connectivity, but the atoms arrangement in space is different in each of them. And because they have this special property, they interact with the receptors in our nose differently to give us different sensations of smell. So caraway seed oil has kind of an earthy, like a cedar kind of a smell to it. And of course, we know what spearmint is. Now, the other type of isomerism that we have here is called geometric. This is one of the last ones that we're going to look at here. So geometric isomerism. So this is caused by a restriction in rotation. And that can occur for two things that come up. So it can occur from carbon-carbon double bonds and from cycloalkanes, which simply means that you have carbons connected in a circle. Cyclo is a circle, alkane just means you have CH parts essentially. So let's take a look at both of these for a second. So in the first case down here, we know that molecules can't rotate freely around carbon-carbon double bonds. So when we build this double bond here, like when we look below at this molecule, so here's our pi bond. And by the way, this is the way that we often draw pi bonds rather than having them kind of come out and down like that. So those become kind of tricky to draw over time. But in order to do a rotation, that bond would have to break. So we're not going to break that bond. Is it possible to break it? Yeah, but it doesn't have free rotation. You got to put some energy into it in order to make this this bond rotate. Right? Where if we have something that's sp3 hybridized like this, each of these carbon atoms has free rotation. Hey folks, so I wanted to take a second and show you some of the models that I made. Let's take a look. Alright guys, so we have a few molecules here. Here is that molecule CH3CH3. And you can see that on one end we have total free rotation, right? So there's an energy to do this, but we don't have to break any bonds. So we have free rotation there. Where if we look at our carbon-carbon double bond, right, there's your standard double bond. If you take this and try to twist it, you're not going to be able to twist it, right? And these little bumps here represent our pi bond. Right? Here's kind of an organic chem model set of this. So here's your p orbitals making a bond here, and the other half of your pi bond. The same deal. We can't get any rotation there. We can't twist these things unless we pop off a bond and do a rotation. And that thing is going to cost energy. So no free rotation at room temperature with that. Now, because that rotation is not possible around those carbon-carbon double bonds, some of these molecules, right, these things are called alkenes, by the way. So some of these molecules are going to display something called geometric isomerism. So if we look down here below, here is an example. So are these two molecules the same? Remember that we can't free rotate. So in this case, we can pretty easily see that the bromines are on the same side. And here, they're on opposite sides. So we can't flip-flop around this carbon-carbon bond. So this rotation is not possible. So we can't alternate places between these two without breaking that carbon-carbon bond, right? So it's like the Molly-Mod kit. When you make this thing, you'd have to physically, right, pop out a bond, swing it around, and right, connect it back in. And that's something that doesn't happen at normal temperatures. Now, to name these molecules, we have to distinguish whether or not we have similar groups on the same side or if they're on opposite sides. So there's a nomenclature part that comes in. Nomenclature just means how do we name something. So that there's going to be two outcomes for this geometric isomerism. For right now, we're going to see cis or we're going to see trans. So here's what we're going to do. It's just two simple rules. It's pretty straightforward. We're going to examine the four groups attached to the carbons of the alkene. Right, so when you look back up here at this example, here are four groups, right? 2 bromines, 2 CH3s. Right, now, when we look at that, and I'll go ahead and I'll just circle all of these just as an example, two things need to be mentioned. We must have exactly 2 identical groups. So 2 of those groups have to be identical. So if there was 4 different groups there, we can't use this. And one of those groups has to be on each of our carbon atoms. So they can't be on the same carbon atom. And then we're going to compare the relative locations of the 2 groups that are identical to each other. Okay? And we're going to have one of two outcomes. All right, so what we're going to see is if we're on the opposite phase. So if we look at this example down here below, here's a chloro group, here's another chloro group. So those are the same, right? And they're on opposite faces of the carbon double bond. So in this case, we call them trans to each other. It's true that this methyl group here and that this other CH3 methyl group are also identical, so we could use that and also identify this as being trans because of those groups. But again, we're looking for two groups that are identical. So here's a chloro group and another chloro group, just like before. Here they're on the same side. So same side means cis for us. Now soon we're going to learn how to name these molecules. And what we would say is it's going to be cis, blah, 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 or trans, the same name. So this cis and trans is like it's a little indicator that we put in front of the name to indicate where the two groups that are identical are located, same side or opposite side. If we look at this next example, let's see, can we use it? So we have a chloro group here and we have a chloro group there. Great, there's two. But here's three. So cis and trans here is not applicable. We can't use that terminology. So the last one to look at here is this molecule. Here we have 1, 2, 3, 4 groups. Right? So interestingly, and they ask this question sometimes in textbooks, and it can be confusing. So we can't use cis trans to name this molecule, because to be cis or trans we have to have two, right, identical groups. And we don't, we have 4 groups. But if we have 4 different groups, the molecule does show geometric isomerism. And the type of label that this is going to get is something called E and Z. And that is something that's going to be covered later this semester. So you're not going to worry about that right now. So you're not going to stress about this. However, there's going to be a question or two that shows up where they ask, does this molecule display geometric isomerism? And the answer is, yeah, that one does, but you can't call it cis or trans. So I think there's like 1 or 2 problems in your textbook where this kind of creeps in. Now, the other place that you actually see cis or trans is in rings. So if you look at a cycloalkane and imagine it, right? So of course, if you look at something like this with 6 carbons, now this is a flat molecule as I've drawn it, but if you build this molecule, each one of these carbons is going to have a wedge, something coming out, and a dash. So there's this front face, and then there's this back face, kind of substituents at each one of those positions. And if you take the molecule and you kind of rotate it and put it on its side, we can see this a little bit more clearly. Right? So we would call this maybe the top face, right? And maybe down here is your bottom face. So it turns out in rings we can't twist them without breaking bonds either, right? Just think of a hula hoop. You can't take it and twirl it around 180 degrees, holding one side right steady without breaking the hula hoop, essentially. So the 2 outcomes are the following. So if we look at 2 atoms that are on the same face, we call them cis to each other. So all the atoms, in fact, up here on the top, are cis relative to each other. And then all the atoms down here, because they're on the same face, they're on the bottom face, are going to be cis to each other. All right, so in a ring structure, what that means is a dash, dash, or a wedge, wedge. So both of those are going to lead to cis. So then how do you get trans? Well, trans just means you have something on top of the plate and something on bottom of the plate, essentially, right? So this atom right here, relative to that atom down here, those are trans to each other. And on this flat structure here, trans would be a wedge dash or a dash wedge. So those together give us trans. All right. Now if we look down below, let's take a look at it. Now the other thing to point out for the rings here, there's a requirement. So notice here two substituents. And then the other thing is that those substituents do not have to be identical, as in this alkene nomenclature. If you have more than 3, then you can't use cis or trans for the rings. So if we look down below here, and look at this first molecule. So here's a bromo group, a bromine atom, and here's a CH3 atom here. Those are both on wedges, so wedge, wedge, cis. And that's straightforward. So here's a chloro group, that's on a wedge. Here's a CH3 group here, that's on a dash. So that's a dash and a wedge. And that is trans. And here we have 1, 2, 3. So cis trans is not applicable. So you may wonder, well, how do you indicate stereo? How do you indicate their position or stereochemistry? It's something we'll talk about later on this semester. So you're not going to worry right now, but you would just say that you can't use cis or trans for that guy.